We're going to take a look at some switching fundamentals. Should be familiar to you from your CCNA studies, but you definitely want to review it before we go on to the NP switch exam. And also some new stuff as well. But before we proceed, a moment of silence, please, for the two old friends you see on the screen. And if you're wearing a baseball cap, please remove it. Thank you. In all seriousness, we are not going to spend time discussing floppy disks, and I promise this is the only time you're going to see one of those in this course, or probably any other course you ever get of mine. But the item on the left is a hub, and that's the predecessor to today's switches, and we need to know how hubs operated, why switches are such an improvement over hubs for your exam, but it's also good to know for your job knowledge as well, your personal knowledge set as they call it. Now you will also sometimes see a double-headed arrow on top of the icon representing a hub. The only thing I can even imagine on your exam is they show you an exhibit and you've got some switches in there and all of a sudden you got this thing with one arrow on top. Well, what's that? Well, you know it's a hub. And once upon a time, back in the day, however you want to put it, our hosts actually had to share transmission media via a hub. Can you imagine such a thing? Actually, we got through it, and CSMA-CD is a big reason why. Because with one big collision domain, and that's what we have here, we had to have rules on when a host could transmit data. Because if we didn't, one host's data would almost continually be colliding with another host's data, and you can imagine if you had more hosts than 3 connected to it, you'd have collisions all the time if you didn't have a set of rules. And when we have that collision, the hosts have to retransmit the data, which is more work for them, slows the overall process down, and of course, there would be no guarantee that another collision wouldn't occur when that retransmission occurred. Now, the set of rules for transmitting Ethernet via shared media is Carrier Sense Multiple Access with Collision Detection. And thankfully, with that long-winded name, we refer to it as CSMA-CD. And here's the overall process. A host with data to send, the first thing it has to do is what we call listening to the wire. And that means it checks the shared media to see if another host is currently sending data. Now, if the media is in use, the host backs off for a few milliseconds before listening to the wire again. And if the media is not in use, then the host will go ahead and send the data. If two hosts happen to send data at the exact same time, the voltage on the wire will actually change, and that indicates a data collision to the sending devices. Now at that point, the hub might as well be a bomb, because what's going to happen is the data involved in the collision is going to explode when that collision occurs, and it's absolutely unusable. So this is what we end up with. Even with CSMA-CD, we were going to have data collisions. It's just that CSMA-CD helped us reduce the number of collisions. Now back to the overall process of CSMA-CD. When the sending hosts detect that voltage change, they go, oh man, we got a data collision. So they send a jam signal, which indicates to other hosts on that shared media that they should not send any data right now because there's a little bit of a problem. Now the sending host will then invoke a back-off timer, and that is set to a random number of milliseconds. And when each host back-off timer expires, they begin the CSMA-CD process from the very beginning by listening to that wire. And since the back-off timer is set to a random value, it's very unlikely the data collision is going to occur. Now, if this sounds really inefficient to you, especially if you've come along after this and you've only worked with switches, then yes, it was inefficient compared to what we have now. But these built-in delays at the time, they were a small price to pay for being able to share that media. And you're thinking about 4 minutes in, Chris, this is all fantastic. What does it have to do with switching today? What's it got to do with my exam? What's it got to do with anything? Well, hang in there with me, because what wasn't around when we had CSMA-CD? Well, voice and video conferencing, YouTube, Vimeo, voice over IP phones, all kinds of ultra delay sensitive voice and video traffic is commonplace in today's network. And we were only dreaming about this stuff back in the days of the hub. Having one big collision domain, it's not even an option. It just wouldn't simply not do today. Now, what typically networks today have is something like this, where you have 3 hosts connected to a switch, and we have 3 collision domains. Because a separate collision domain is created for each host, because each port on a switch is its own little collision domain. Collisions literally can't occur in there. Now, Cisco's documentation, some of it I should say, refers to this one host, one collision domain ratio setup as microsegmentation. It's not a term you hear often, but I bump into it every once in a while in Cisco books and especially their PDFs. And you just stop for a second, it's like microsegmentation. That's just one host, one collision domain, as we've seen here. Now, also, thanks to our switch, we get a lot more bandwidth than we used to get. And with all that voice and video flying around, we'll take all the bandwidth we can get. Because when hosts are connected to individual switchboards, they don't have to share bandwidth with other hosts. And with the right switch config and the right network cards, each host can theoretically run at 200 meg per second, 100 sending, 100 receiving, and that is assuming fast Ethernet ports, which most ports on modern Cisco switches are. Not all of them, but the ones we'll be using here are capable of fast Ethernet speed. Now, that takes care of the collision domain issue, but we still have another problem with having one large broadcast domain, because by default, a broadcast or multicast sent by any host connected to that switch is going to be received by every other host on that switch. That is a lot of unnecessary broadcasts flying around the network. And that in turn means unnecessary work, not just for the switch, but also for the hosts. It's okay for us to concentrate mostly on the switches because after all, we're prepping for the CCNP switch exam, not the CCNP host exam, which doesn't exist. But we still have to be concerned about our end hosts, and we don't want them getting a lot of broadcasts and multicasts they don't need because they still have to process them, or at least begin to process them before they realize, hey, wait a second, I don't even need this. And broadcast domains, we're going to come back to that in the VLAN section of the course, which is huge and plenty of lab work there. But VLANs are what we actually use to break up our broadcast domains. Now, I want to go over these frame forwarding decisions with you. And because when a switch gets a frame, it's going to either forward that frame, filter it, or flood it. But before we get to those, and don't peek at the board for the answer, when a frame enters a switch, what common value does the switch look at first? Someone asked me that a long time ago, and I was like, well, the destination. Because the switch, that's what it wants to do. It wants to get the frame to the right place. So it's going to look at the destination address because that's the only way to get it where it's going, right? Well, that's going to happen eventually, but that's not what happens first. The switch actually looks at the source MAC address before any other value. And your logical question to me saying that could be, or likely is, well, why does the switch even care where the frame came from? Well, the logical answer is because the source addresses on those incoming frames, that's how the switch builds and maintains its MAC address table. That's not the only reason for this behavior. We'll see at least one other in this course, but it is a major reason. Thing is, our routing table, it's helped along by dynamic routing protocols. We might put a few static entries in there, but generally we're going to let a dynamic routing protocol like EIGRP or OSPF build our routing table because frankly it's just a lot more efficient. Well, there really is no equivalent to these protocols at layer 2. We're going to see some layer 2 protocols, but none of them are absolutely dedicated to building the MAC address table. So the switches have to do that in another way. Now, we could build a MAC table with all static entries. We could do that. I have a baseball bat over in the corner of my workspace here, and I could take that bat and hit myself over the head with it. But there are consequences to that I might not like. I feel the same way about a MAC address table with all static entries because it's just so much more work for you, and the more manual configuration you do on any device, the larger the chances of misconfiguration. I personally am a really good typist, but the more I type, the more the chance there is a typo gets in there. That's just the way it is. The more you do something, the more the chance of a mistake. The more information you add statically, the greater the chance of a mistyped entry, and not only are you not getting the desired result, you're creating more troubleshooting for yourself, and that's really the last thing we want to do. Because if a port goes down and we switch the connected host to a good port and we're using all static entries, we wouldn't even have full connectivity until we add a new static entry for that host MAC address. Not the hardest thing in the world, but in the heat of battle, it's easy to, first off, mistype the MAC address in the static statement, and two, to forget to remove the old entry, which leads to even more unnecessary troubleshooting when that bad port is fixed and another host gets connected to it. When you have a choice between letting the switch or the router do the work and you and I as the network admins doing the work, we should let the hardware do it every single time. It doesn't make us lazy, it makes us smart because it's almost, I have to say almost because there's got to be an exception somewhere, but it's almost always much more efficient to let the router and the switch do things dynamically rather than you and I trying to keep up with static configurations. And in an enterprise network or even a medium-sized network, you're going to do everything statically. You know, it's just, to me, it is futile. It's a waste of time, and especially when we have tools that very easily can do the job for us. Now, I want to go through, we're going to do a walkthrough next, and this is how a switch builds that all-important MAC address table, and we'll also see each of those frame forwarding options in action. Just a quick word to those of you who are taking your first course with me. We do a couple of these walkthroughs, and you'll see why here, because first off, the topology is not exactly real world, but we're also using some MAC addresses that are a little easier to work with this walkthrough. There are plenty of live labs on live Cisco equipment coming, believe me. I just want you to know we don't just look at pictures in this course, believe me. We've got at least 40 or 50 labs, probably a lot more than that, that we'll be using on live Cisco switches and layer 2 switches and multi-layer switches. But this one I want to do on the board because it's a lot easier to follow. And in this diagram, we have 4 hosts, we have 1 switch, and we have 1 hub. And hosts A and B are connected to the hub, and in turn the hub is connected to our switch. The MAC address table of each host is the host letter repeated 12 times, 12 A's for host A, etc. But between videos here, because I'm going to stop this one in a moment and we'll go through the walkthrough in the next video, please write this out because we are going to come back to the diagram, but the switch port numbers shown here on the Cisco switch 0/1, 2, and 3, they are not going to be repeated in subsequent drawings because we're going to have arrows and frames flying everywhere plus some addresses, and it just gets too cramped if we leave those there. So write this out, and please note that fast 1 or O/1 leads to A and B, O/2 leads to C, and O/3 leads to D. I'll see you on the very next video, and we'll get started with that walkthrough.